Hi everyone, welcome to my channel. So today we're going to see the basic model of CNN layer CNN algorithm for deep learning. So it is the first model where where the scientists they got the first breakthrough to have learnable kernels. So before that they were using hard coded values for all the kernels. So they if they have to get any distinct features, they have to apply the distinct hard coded kernels. So actually, from for in 1998, Jan LeCun, previous Benjo and co-scientists, they they published a paper regarding LeNet-5. So they have actually have some different convolution layers, and they have applied interconnected kernels. Like they have separated two layers, they divided two layers. One is CNN layers, and one is normal feed forward networks. So in that particular layers, they interconnected every kernels images as well as the neurons to while doing backward propagation. They have to update the or they have to learn the kernel values as well. Okay, so we are going to see how the architecture is going to be for LeNet-5. So Lee LeCun actually Jan LeCun is basically one of the renowned scientists. Actually, he recently received uh, a Turing Award, that is called the Nobel Prize for Computer Science branch for their work on the deep learning. So let's see. So what is the history behind it? So it is basically used to automatically classify the handwritten digits on the blank checks in the United States. So earlier they were working on particular use case where they have to classify the pin codes written in the like in the letters to identify the pin codes. So they were working on that. So by that time they actually got the breakthrough using LeNet-5. So it was invented for character recognition. Earlier, actually, character recognition had been done by manual feature engineering or machine learning algorithms to classify them. So basically, some KNN classifier or SVM classifier. So I suppose you guys know about machine learning. So it was done by the machine learning algorithms. So now, actually, as we know, the network learns the best representation for the raw images automatically. So we're going to use that. So this is the basic structure of, or you can say basic architecture. So this is the very it is not at all difficult, it is very much easy architecture. From this actually all the advanced neural networks or urban computer vision started. So this is after from 1998. Actually the next advanced layer that you can say AlexNet has been started for 2012. So it is the basic layer, like basic learnable kernels or basic architecture started from this. All the advanced chain algorithms have been proposed by scientists. So let's understand it. So it has, as you can see, it has seven layers, three convolution layers. So three convolution layer. So you can say this is one convolution layer. So this is second convolution layer, and this is third convolution layer. So convolution layer is nothing but we have some image, input image. So we apply filters. Then after applying filters, whatever features we have extracted, that you can say the convolved image or convolved features, right? So we have such three features and the subsampling, two subsampling layers. So here we have applied subsampling means you can say we are using pooling features. So maybe max pooling or average pooling. Here at the time of testing by Leku 1998, the max pooling was not invented, so they have used average pooling. So here one average pooling they have used, and again S4. one average pooling here is there, so S4. So this one is average pooling. So they have used two average pooling, three filters, and three filters means three convolution layer and one feed forward network. So F6, this is feed, this is the feed forward network, you can say. So here C5 is also applied to the, like it is flattened layer, you can say. It is also a neural, like it is connected to the neural, like feed forward networks. So okay, so this is the basic structure that has been given in the tabular manner, so it is very much easy to understand. This is the input image. So A is nothing but the input size 32 32. So at the time of testing, the image dataset, the image was 32 cross 32, but now it has changed while testing. While showcasing the code, I'll show you guys how it is changed. The current image dataset image has been changed to 28 cross 28. So the time of testing, it was 32 32. So as you can see from the table, so input image was 30 cross 32. So feature map is 1 means it is a gray size, like gray color image. So we have only 2D data, right? 32 cross 32. So if it had been color data, then we would have used RGB or three-dimension data, right? So it is just a gray image. So yes, 32 cross 32. And why we have convolved, this is a convolution layer C1. So we are by applying 5 cross 5, like 5 cross 5 kernels, we got 6 20 cross 28. So by applying 6 cross 5, like 6 5 cross 5 kernels, we got convolved features, 6 20 cross 28 convolved features. So how we got 28? So 20 is nothing but there is simple formula, like as for now. Just remember this formula. Going forward, the formula will change a little bit, but as of now we are applying 32. So the input is 32. So the filters, so filter minus filter plus stride. So input is 32, filter is minus 5, plus stride is 1. Stride is nothing but it will slide towards the columns and rows, you can say vertical or horizontal, right? So one stride means it will move just one one towards columns and one towards rows, right? So 20 is nothing but 32 minus 5 plus 1, so 28. So it is convolved to 28 into 6 convolved features. So after that, what we have used, average pooling. So here we have used average pooling. So 2 cross 2 average pooling is used. So yes, 2 cross 2 average pooling is used. So 28 cross 28. So 628 cross 28 is there. So it is pooling. So it has been reduced to 14 cross 14 into 6, because we have applied pooling. Pooling means we have extracted 2 cross 2, 2 cross 2. So from 2 rows and 2 column, we have just taken 1 pixel. From 4 pixels, we just average out all the 4 pixels, and we get the single pixel values, and we keep in the um, convert, or you can say extracted features. So we got 14 cross 14 uh, extracted features. Then we convert using 5 plus 5. So there actually we have used 16 5 plus 5. So the number has been increased to 6 to 16 here. So 16 10 cross 10, 16 10 cross 10 filters. So no, sorry, 16 not 10 cross 10 filters, 16 5 cross 5 filters. So after applying 16 5 cross 5 filters, we got 10 cross 10 into 16 feature maps or extracted features, right? So how we got 10 after 14? Because 14 is the number of input image. So 14 minus filter, what is filter? 5. 14 minus 5 is what? 9, plus 1. 1 is stride, right? Plus 1. So stride is 1, so 10. So 10. 10 cross 10 the pixel values or the feature maps we got after applying 16 kernels, because as we have applied 16 filters, so we got 16 feature outputs, right? Then we have applied average filling here. Average filling, after applying average filling, 10 will be converted to half, so 5 plus 5. So yes, so 16 10 cross 10 was there, so after dividing by 2 or just extracting half of the pixel, so it would be 16 5 plus 5. So then actually we need to flatten the data. So how the flatten will happen, so I will tell you in the next slide. So flatten the data, or you can say convolute. So how actually it flattens the data, so it actually applies one more filters, like at the same size. So it was 5 plus 5, so 5 plus 5 filter is been applied, so 5 minus 5 plus 1, so 1, so 1 cross 1, so it has 120 features with 1 cross 1 size. So next, the feed forward network, so we have applied 84 neurons, and for last layer, that is the output layer, so where we have to predict, this is the output. So we have, as you know, the short function is for the multi-class classification, and and what is the significance of all these activation layers, so I'll show you while like when I'll show the code. I'll tell like how the like what is significance of the 120 neurons, 84 neurons, or 10 neurons, what is significance, I'll show you in the code. Okay, so as we know, like why we need such like so much convolution layer. We have image, we can directly put to the network and get our digital output, right? So like why we need to extract features for like so many uh, convolute features to apply in the feed forward network. So yes, actually from the first, like after applying the first filters, we get the first features. First feature nothing but we try to get some dot, like for different filters it will try to extract the minimum feature, that is dot, small dots. Then after using various features, maybe they have tried to get diagonal features, try to get some straight line features, try to get some circular features. So then like after feature, like after convolute layers by layers, they want to get some complex features in the single email, like uh, all the complex features will be put in the flattened manner, and all you see, as you can see, this is the flattened manner, this is the 120. As you can see, the 120 layers has been connected to this flattened layer. So it has been flattened means all the features uh, has been straight up to the single column, and it has been connected to the neurons. Each feature is nothing but maybe straight line, maybe circular, maybe diagonal, maybe hyperbola. Like all the complex features has been connected to the feed forward network. Okay, so this is all about theoretical explanation. I'll show you the code part on the next video. Thanks. Thank you. Thanks for watching.